Hello everyone. Today I'll be working through question 6 from the practice final for the Physics 457 upcoming final exam. I'm choosing to start with number 6 for my filming purposes, but also because if I were to be writing this exam, I think that number 6 is, for me, the easiest question to solve. It just involves some mathematics and some derivations and just kind of proving something that you should probably know just based off the formula that you're given. So when I see a final exam, I usually flip through until I see a question that I know how to do, and I know how to do it well. And I started with that question just to give myself a little bit of a confidence boost, also save time near the end, knowing that I finished the questions that I know how to do. And I think that it's just a good practice to start with the questions that you know, and then work towards the more difficult ones. So I'm starting with this for filming purposes, and also that's kind of my mindset when I'm thinking about starting a final exam. So question 6 reads, expressions are given below that describe a function in a region of space. The units to make all of these expressions work properly have not been explicitly written out, but they are present. And then there's two parts. In A, it says which of these expressions satisfy the wave equation. Explicitly state whether each expression does or does not satisfy the wave equation. And part B says find the wave speed for whichever expressions satisfy the wave equation. And then there's four functions, f1 to f4. So instead of working through A and B separately, what I'll be doing is I'll be working through each function individually and proving whether or not it satisfies the wave equation, and then finding the wave speed for that function. So we'll start with f1. And f1, sorry, this is question 6. f1 is a function of r and t, and it's given by the exponential of the k vector, which is the wave vector, dotted with the r vector, spatial vector, plus time over some t. Okay, so that's the function that we're given. And we wanted to prove whether or not this function satisfies the wave equation. So for all of the coming problems, we're going to be using this wave equation. So we will recall just what that wave equation is. And in 3 dimensions, it's given by the Laplacian of our function is equal to 1 over some speed v squared, which is the speed of the wave, the second derivative of the function with respect to this time squared. Okay, so for this function, we want to plug it into this equation and see if it satisfies the requirements. So some things to note right away are that this is in an r vector, which is just our normal position vector, x, y hat, and z hat. And our k is our wave vector, which denotes the propagation of that wave, and it's given by some x, some kx and x hat, ky and y hat, and kz and z hat. So they don't explicitly give us k and r in this problem. However, we do know that just kind of the general form of these two equations, and this might help us in the coming derivatives. So I'll do this dot product first between these two vectors. So k dot r, and I'll find out we get kx x plus ky y plus kz z, given that the dot product, the x hat components go together, y hat and z hat, accordingly just a normal dot product. So again, this part isn't really given in the problem, but I think this is a really good way to visualize what's actually happening in this exponential. And then when we start taking our spatial derivatives, we'll kind of see why we can pull out certain things from the exponential that we do. So we have k dot r over here. And now we will recall again just that the Laplacian in our Cartesian coordinates is given by d squared by dx squared plus d squared by dy squared plus d squared by dz squared. So these are the specifics for this problem given the coordinate space that we're in, as well as k dot r. Even though they're unknown, we can still write them in that way. Okay, so we'll start with the left-hand side of this wave equation, and we'll see that the Laplacian of f is given by the Laplacian of our function, the exponential of k dot r plus t over t. And this, of course, is when we substitute these formulas in, the second derivative of x, second derivative of y, second derivative of z, all of this big expression now, which is the exponential of k dot r, which is over here, kx, x plus ky, y plus kz, z plus t over t. Just change pens here so we can see what's going on. Okay, so now we take the second derivative, spatial derivative with respect to each of these coordinates, and we can see right away that the x term will not affect any of these constants in the exponential, so we'll just end up with a kx squared coming from this first term. Okay, and then it'll also be multiplied by the exponential because that's how derivatives of exponentials work. However, I'll just factor that out towards the end. So then we have a d squared by dy squared, which takes care of this ky squared, and then similarly for the kz squared. And then this is all multiplied by our exponential kxx plus ky y plus kz z plus t over t. Now once again, just to kind of show you what my thinking was, the reason that I expanded out this k dot r, this dot product right away, was to see that each of these individual components has an x, a y, and a z. So when I take the second spatial derivative with respect to x, y, and z, I can just immediately pull out the coefficient in front, which is the kx, the ky, and the kz. And I get a squared term from each of them because I take the derivative twice. So I'll get a kx down, and I'll pull another one down in the second derivative. And now this term here is actually interesting because if we take the magnitude of k squared, which is just k dotted with itself, we find that this actually gives us kx squared plus ky squared plus kz squared according to dotting this vector by with itself. You can check that at home. You get kx squared plus ky squared plus kz squared. So we see that this is what we have in the equation here. So this becomes the magnitude of our wave vector k multiplied by our exponential. Here I'll just write it again as k dot r to save some space plus t over t. So that's the left-hand side of this equation. This Laplacian of f is the Laplacian of our function f1. All right, f1. All right, so now we'll look at the right-hand side, which is 1 over v squared, the second spatial derivative, second time derivative of f1. And this is just 1 over v squared, and we take the second time derivative of our function, which is exponential of k dot r plus t over t. And this, of course, we get the derivative of t over t twice. We get 1 over v squared, 1 over t squared, exponential of k dot r plus t over t. Okay, so now we can equate these two sides. We have the left-hand side of our wave equation and the right-hand side of our wave equation. And we'll see that if we take a look at this piece here and this piece here, they have a common factor of f1, so our function. So that means that the function f1 is still present on both sides. So essentially when we equate those two, it's not that it's going to cancel, but they're going to be equal at all points in space. So what we're left with is that the magnitude of our wave vector squared is equal to 1 over v squared, 1 over t squared. And that's what we want to look for when we're trying to see if this satisfies the wave equation. What we say is the function satisfies the wave equation is if it satisfies this formula up to some constant. And that constant is given by the velocity of the wave. So we can solve this for v. Get v squared is 1 over the magnitude of k squared t squared, and that the wave speed is 1 over the absolute value of k times t. So just to recap, we started off with our function f1. It's a function of r and t, where r is our Cartesian spatial vector, and it's given by the exponential of our wave vector k dotted with our r vector plus some time over some constant big T. And we right away know that our k vector and our r vector are arbitrary in this case, but we can write them in the normal way where we have x hat, y hat, and z hat for the r vector, and then kx, ky, kz all in their respective coordinate vectors for the k wave vector. Take that dot product and we get this expression here. Again, this is not really needed for the problem. You can take the Laplacian of k dot r as it is. However, I think it's easier to visualize and see what's happening as soon as you write out this double derivative and can see each component and why we get these individual k components down for each derivative that we take. This, of course, is the wave vector, the magnitude of the wave vector, so it's k vector squared, and then we can write out the exponential on that side, and then we take the second derivative of the time vector on the right-hand side. We can see that, of course, we get 1 over t squared down. We still have this function on this side. That'll be the same on both sides, and of course, f1 satisfies the wave equation. And then we can solve for the velocity with which that wave is propagating, and it's 1 over k vector times the big capital T. For part 2 of question 6, I'll be working through the second function. So the second function is f2. It's a function of r, the r vector, and t, and it's given by the cosine of x hat plus 2y hat minus 2z hat, so that's just our k vector. We know that it's essentially similar to f1, where we have our k vector dotted with our r vector, but here the k vector is given by explicitly by x hat plus 2y hat minus 2z hat. It started with the r vector squared, the whole thing squared, k dot r squared, and then it's minus 6t squared. And again, we'll be trying to see if this function satisfies the wave equation, which I have left up here. So it's the Laplacian of f is equal to 1 over v squared times second time derivative with respect to f. So this expression is kind of gross, and this dot product is even worse, so I don't want to expand that right away. So I'll start with the right-hand side of the wave equation this time and take the second time derivative first. So we'll start with that, and we'll see that we have 1 over v squared, and we'll take the second time derivative with respect to f2, and this is given by 1 over v squared d squared by dt squared of our function, which is cosine, and here I'll just write k dot r to simplify things. This is our k, minus 6t squared, and all the brackets are in. Perfect. So now we'll take this derivative with respect to t, and the first derivative gives us, by chain rule, negative sine of k dot r squared minus 6t squared times a negative 12t. And again, that's by chain rule. We take the first time derivative with respect to cosine, which gives us a negative sine times whatever was inside, and then we take the derivative of the t term inside of the cosine, which gives us a negative 6 times 2. We bring that vector down, and we have a t. So now when we take the second time derivative, we see that we get the first one is with respect to sine, so we'll get a negative cosine of k dot r squared minus 6t squared, again multiplied by this inside term negative 12t, and this is all multiplied by the original negative 12t by the product rule, and then we add now a negative sine of k dot r squared minus 6t squared with the derivative of this with respect to t, which gives us a negative 12. And the last bracket will be there, and then one here. All right, so to recap what I did quickly, I take the second time derivative of our function f. We see that it depends on a cosine term, so that becomes a negative sine term, and then by the chain rule, we pull out this negative 12t from the derivative of t within that cosine term. The second time derivative then is a product rule because we have sine depending on t, and also this variable t on the outside. We can expand this out, take the derivative, and we get negative cosine of what was inside, multiplied again by the chain rule of our negative 12t. We have a negative 12t here, and then we have our second term. So to simplify this, we'll just write one more line and then talk about it. So we have 144t squared with a negative sign, cosine of k dot r squared minus 6t squared. And then this will be negative and a negative cancel, so we get plus 12. Sorry, I forgot a t in my derivative. Sorry, no, never mind, that was because of the product rule. Again, when I took this derivative, I got rid of the t, so that should be just a negative 12. Negative and negative cancel, and we get sine of k dotted with r squared minus 6t squared. Okay. So now, of course, to continue on, what you could do is you could take the Laplacian of the function on the left-hand side of that equation, take the Laplacian of this, which would be our k dotted with our r. Again, you can expand it out like we did for the function 1, where you say x hat, y hat, z hat for the r vector. See that you can take your second derivative with all those terms. However, that's going to be quite time-consuming, quite challenging, and also super prone to mistakes. Before we do that, I mean, we could do that and you could prove to yourself that yes, the left-hand side will not equal the right-hand side, but I will try to convince you, without doing that math, that just by looking at this expression with respect to the time squared, you can see that right away, and you don't have to waste your time doing that derivative. So again, the reason I started with doing this time derivative first was because I knew that the Laplacian, the spatial derivative of k dot r, was going to be much more challenging and difficult and complicated, just based off of seeing that I had this k vector with this r vector, and that was squared. So again, there would be multiple chain rules there when you're taking the second spatial derivative. However, this time piece is by itself, so that might be an easier place to start. And then what we ended up with was essentially a solution that has a sum within it. So we have a cosine and a sine, and this term depends on t squared, and then this term is just dependent on sine from our original function. But what we can see is that when we take the Laplacian, the spatial derivatives of this cosine term, we will never pull a time outside of that cosine term, because when you take the derivative with respect to this, there is no time within this k dot r vector position of our cosine term. So because we see this time squared term, when we take the Laplacian of f, we will never get a t squared, a term with a t squared attached to it. What that means is that we'll never be able to multiply by some constant in order to get the left-hand side equal to the right-hand side. So we can see right away, because this piece has this time squared attached to it, that we will never be able to have a left-hand side equal to the right-hand side of our wave equation, and then f2 does not satisfy the wave equation. So in my notes I said that this t is very important, this t squared is very important, as taking a spatial derivative on the left-hand side will never produce a t outside the cosine, so this does not satisfy the wave equation. So again, we don't have to find the wave speed v, because there is no constant that will make the left-hand side equal to the right-hand side. Okay, continuing question 6, we now look at f3, our third function. We want to see if it satisfies the wave equation. We can see right away that f3 is a function of s, phi, z, and t. So that to me screams cylindrical coordinates. That's a really big pickup right away, so that we know what kind of Laplacian to take the derivative with respect to, what kind of coordinate system to use. We see that's a function of 3s squared minus 5 phi plus 4z plus t squared. So again, now that we know we're in cylindrical coordinates, we can write our Laplacian, which you can get from your formula sheet. It's given by 1 over s d by ds of s d by ds plus 1 over s squared d by d phi squared, second derivative, and then plus d squared by dz squared. Okay, so this Laplacian is now in cylindrical coordinates because our function is cylindrical coordinates. So we're going to do the same thing where we take both sides of the equation and try to see if we can equate them. So we'll start with the right-hand side. See that 1 over v squared d squared f3 by dt squared is given by 1 over v squared, and then we take our function d by dt squared of our function, which is 3s squared minus 5 phi plus 4z plus t squared. And this is 1 over v squared, and then the second time derivative, so all of our spatial coordinates will go to 0 because there's no time dependence, and we'll get a 2 times t, that's the first derivative with respect to that, and then we'll get 1 over v squared times 2. So this is equal to the right-hand side of our equations, 1 over v squared d squared f by dt squared. Okay, so now the left-hand side of our equation, we'll start way over here since we have to write a big expression. We'll see that we want the Laplacian of our function f3, and this is given by 1 over s d by ds, s d by ds, plus 1 over s squared d squared by d phi squared, plus 1 over v squared, sorry, that's from this term here, so I'll erase that. Get confused here. Plus d squared by dz squared of our function, which is 3s squared minus 5 phi plus 4z plus t squared. So doing all these derivatives at once, we see that we get 1 over s d by ds of s times all of these variables with respect to s. When you take the derivative with respect to s, they will go to 0. So we're left with 6 times s and then we add on 1 over s squared, and then we have the derivative with respect to phi. Again, all of these variables without a phi dependence will go to 0, so we just get a negative 5 with respect to phi, plus the first derivative with respect to z, which just gives us a 4. Okay, then we take the second derivatives. Now we have 1 over s, and then 6 s squared. Take the derivative with respect to that is 12s, plus 0, as these are just now constants. So what we're left with is that this is equal to 12, and this is our Laplacian of f3. Okay, so now if we equate the left-hand side and the right-hand side, we will see that we get 1 over v squared d squared f by dt squared. The third function is equal to 2 over v squared is equal to 12 is equal to the Laplacian of f. And so we see that f3 does satisfy the wave equation, given that we can start with the left-hand side and end up with the right-hand side. So we have this expression here, and by solving for v, we get v squared is equal to 2 over 12, and v is equal to 1 over the square root of 6. So again, just to walk through and recap what we did for f3, we see that f3 is a function of s, phi, z, and t, and it's given by the variables here. And we can right away pick out that it's in cylindrical coordinates, given that it's s, phi, and z. So then we know when we take the Laplacian for our wave equation, we end up with the Laplacian in cylindrical coordinates, which you can get from your formula sheet. And then we do the left-hand side and the right-hand side. So the right-hand side, we did the second time derivative here. We ended up obtaining 2 over v squared as our solution. And then when we did the left-hand side, we had this big gross Laplacian derivative. But if you work through and recognize that each derivative essentially cancels out the variables that aren't dependent on that derivative. So in this case, we would get rid of the phi, the z, and the t when we take the derivative with respect to s. Then we end up with our 6s term, continue our derivatives through, and we end up with that we have just the constant 12. So the Laplacian of f3 is equal to 12. And then of course we can see that this satisfies the wave equation because the left-hand side is equal to the right-hand side up to a constant, and that constant is given by the velocity of the wave v squared, which we can solve for as 2 over 12, or that v is equal to 1 over the square root of 6. So again, the biggest thing for this question is just picking out what coordinate system we need to take the Laplacian in, and then making sure we don't make any mistakes in our derivatives. Okay, so we'll wrap up question 6 by looking through the fourth function and seeing if it satisfies the wave equation. So function f4 is a function of x and t only. So we're not working with the r vector from the other problems or the 3 spatial coordinates or cylindrical or anything like that. Here we only have x and t. And the function is given by 2x minus t to the power of 5 plus 4x minus 2t to the power of 3 plus 6x minus 3t to the power of 2. And we want to see if it satisfies the wave equation. So in this case, we just have to strap on our calculus thinking caps and compute a bunch of chain rule derivatives and see if the left-hand side satisfies the right-hand side. So here I want to start with the right-hand side, but again, here I'll just remind us that because we're in one dimension, we only use the x derivative with respect to our function, v squared d squared f by dt squared. Again, just because we're in only that one spatial dimension, so it's a one-dimensional wave equation. So we'll start with I'm just going to change this to right-hand side and get rid of that r vector. And the right-hand side we see is 1 over v squared d squared f4 by dt squared. Now I'm not going to write out the derivative and then the function again. I'm just going to take that first derivative. So we see 1 over v squared d by dt of chain rule here. We have negative 5 2x minus t to the power of 4 plus chain rule 3 times negative 2 gives us negative 6 4x minus 2t squared. And then finally we have a negative 3 and the 2 is negative 6x minus 3t to the power of 1. So that's our first time derivative. Again, this is just chain rules, so remember that you bring the 5 down and then you take the derivative with respect to the inside as well, which gives us a negative 5. Then this goes to 4, and then same thing here, 3 down multiplied by negative 2 gives us negative 6. 2 down multiplied by negative 3 gives us negative 6. Okay, so we continue through second derivative, 1 over v squared. Now we get negative 4 times 5 times -1 gives us a positive 20. 2x minus t to the power of 3. And then now we have a -6 multiplied by a -2 gives us a 12, multiplied by 2 gives us a 24. 4x minus 2t. And then finally here we just have the x term goes to 0, and we get the derivative of 18t with respect to t, which is just 18. Just change pens here again. So yeah, so that in that case, all I did there was take two derivatives with respect to t, and we saw that there was a bunch of chain rule calculus and a bunch of derivatives that hopefully we don't make any math mistakes. Let's check 22x minus t cubed plus 24 4x minus 2t plus 18. Perfect. So now we look at the left-hand side, which is the Laplacian of v4, which again is just the derivative with respect to x of v4, because we're only in one dimension. So we'll do this derivative, and the first derivative gives us 10 times 2x minus t to the power of 4 from the chain rule, plus 12 times 4x minus 2t squared from the chain rule, and then plus 12, 6x minus 3t to the power of 1, all that there. So right away, I am going to pull out a factor of 2 from all of this, just because otherwise my constant terms in front might get big relatively quickly, so I'll end up with a 2. And then I'll go d by dx of 5, 2x minus t to the power of 4, plus 6, 4x minus 2t squared, plus 6, 6x minus 3t. And again, I just did that because I looked at this and I think 10, 12, 12. When I start having taken second derivative, I'm going to pull the 6 out. I'm going to have a squared come down with the 4. I can see that those constants are going to get large right away. So I pull this 2 out, and it helps me for my next derivative, which gives me 5 times 4 times 2, which is going to be 40. 2x minus t cubed. And then here we'll see we get a 2 times 6 is 12 times 4 is a 48. 4x minus 2t. And then here we have a 36, since the t term goes to 0. And again, you can see why if I hadn't pulled that 2 out, those factors would have gotten large quickly. So here, if I pull another 2 factor out, so now I'm thinking I want to make the left-hand side equal to the right-hand side. So I can see here that I have a 20, a 24, and an 18. And I want to make this function appear to look like this function so that I can say that the left-hand side equals the right-hand side, or not, if it doesn't have the same coefficients. So this is 20, and this is 40. So I can see, okay, what if I put another 2 out? So I have 2 times 2, and now I have 20, 2x minus t cubed plus 48 divided by 2 is 24, 4x minus 2t. Okay, that's good. I have 24 here as well. And then plus 18. And then now I can see, oh, perfect. This whole expression here, this function that I left over with, is equal to the one that I have up here on the right-hand side. So I can see that f4 does satisfy the wave equation, because the left-hand side is equal to the right-hand side of our wave equation in one dimension up to a certain constant. And that constant is given by, let's wrap up over here, is given by 1 over v squared is equal to 4. And again, I can see that because this is what I have left over on my right-hand side, and here's what I have left over on my left-hand side. Solving for v, I end up with v is equal to 1 over 2. Or if I were to say, it's going to be the 1 over the square root of 4. And that's the wave speed at which this wave f4 is traveling. So again, just to kind of recap what I went through, we saw that f4 was only dependent on x and t, so it was in one spatial dimension. So our three-dimensional wave equation becomes one dimension in x. This is our function. We took their derivative with respect to the time twice, bunch of chain rule math. Hopefully we didn't make any mistakes, and we end up with an expression at the end. We do the same thing with the Laplacian, which is now in one dimension, so it's just derivative with respect to x. Again, do our chain rule, kind of factoring as we go along to make things a little bit easier and numbers don't get so large. And then at the end, again, what we're trying to find with our wave equations and when we're solving these kind of types of problems is we're trying to see that the left-hand side is equal to the right-hand side. So here's what I have on the right-hand side, and I want to try to express the left-hand side into a similar factor so that I can say it does or does not satisfy that wave equation. So I can see right away this first term, I want to try to make it look like this term here, and I do that by factoring out a 2. And when I do that, I actually find out that all of the remaining terms need to be factored by a 2 in order to be equal to the right-hand side. And then we're left over with the constant in front, which satisfies the wave equation, and that's the wave speed. 1 over v squared is equal to v, or is 4, sorry. And then when you solve for v, you take the v squared up, drop it on the 4, and take the square root, and you get that v is equal to 1 over 2. And that wraps up question 6, which is, again, just taking some derivatives and trying to show that certain functions do or do not satisfy the wave equation. And I would start with this problem personally because, again, it looks like it's just a couple derivatives. If you can remember what the wave equation is and remember what you're trying to solve for or how you're trying to express whether or not a function does or does not satisfy that wave equation, and then what that means to you, and what the velocity or the wave speed that you're trying to find is at the end, this problem is pretty straightforward and just a little bit of calculus.